Hi there. I'll be doing an introduction to computer-aided design and simulation, particularly for chemical engineering. My name is Tufus Manda, and if you have any questions or queries, please contact me on my email address, which is tufusmanda@gmail.com. So what is simulation in chemical engineering? It is an imitation of the operation of a real-world process or system over time. So for example, let's say we have a chemical plant, and within that chemical plant, there's a distillation column. We are trying to imitate the operation of that distillation column within the chemical plant in a computer application. So a more in-depth definition, it is a process of designing an operational model of a system and conducting experiments with this model for the purpose of either understanding the behavior of the system or for evaluating alternative strategies for the development or operation of the system. It has to be able to reproduce selected aspects of the behavior of this system modeled to an accepted degree of accuracy. So that distillation model I spoke about earlier, it has to match the parameters of the plant for it to be valid, and to a certain degree, it can't be 100% accurate. Why do we do simulation? In general, chemical process engineers deal with two types of projects. The first one is design of a new process, and the second one is simulation of an existing process. So process design starts with the requirement for a product and goes through different design steps. So this requirement for a product comes from the market, and we as engineers will then do different steps so that we come up with that product efficiently and also in a profitable manner, right? Whereas simulation starts with a requirement for process modification or optimization and continues with analysis of the existing state of the art. So when it comes to simulation, the distillation column, which I was talking about, we already have it, right? So we are trying to modify it, so that it's more energy efficient, or maybe it produces a product which is more pure. So optimization is increasing the unit operations efficiency. For example, a heat exchanger. There are different types of simulators. Some are commercial, which means you have to buy the license for you to use it. And some are open source, which means you can just download it online for free and use it. There's Aspen HYSYS, there's Aspen Plus, there's ChemCAD. This one you can find a commercial license, which is more robust, or an open source, which you need also to request it from them. There's DWC, and this one you can get it online. Same applies to ChemServe and Coco. My favorite one on the open source is Coco. And when it comes to the commercial ones, is Aspen HYSYS or Aspen Plus. So you need to take note, all process simulation software are developed based on the same chemical engineering principles. So if you master one of them, it is easy to learn to work with the rest in the market or field. Process design. Design is divided into two broad phases, right? That's when you are trying to come up with a new product. So the first one is a conceptual design, including the selection of chemical process, which is the chemistry, technology, which is fixed vessels, fluidized bed reactors, for example, process conditions, like the distillation column pressure as an example, collection of the required data, the vapor liquid equilibrium, issuing process flow sheets, and chemical engineering calculations of equipment. For example, the basic material balance before you start your simulation, and preliminary cost estimation. Basic plant design included a detailed mechanical design of equipment, detailed design of electrical and civil structures, and piping and secondary services is the second part. So steps on the first phase are usually done by chemical engineers, which is the conceptual design, whereas those included in the second phase are done by design specialists or vendors. These are the people who actually provide these equipments, so they supply these equipments. An initial economic and environmental overview helps to exclude most inconvenient methods from further investigation. Also, one should consider local conditions like availability of raw materials. They should be readily available. Possibility of using existing technologies and infrastructure. For example, if you have a boiler within the plant, so assuming I want to design a new distillation column, I should make sure it uses the pressure which is already available. Environmental regulations, these they differ from state to state, and so you should consider those two. Availability of energy sources. For example, if I have a river which is flowing nearby, I can use that water as a cooling source. After the technology evaluations, including environmental, safety, and health aspects, the designer has a short list of cases that need to be simulated using a process simulator to make further decisions. So you need to first go through the technologies initially, environmental concerns and safety. Then you narrow down your research. Then whatever you have after you've narrowed down your research, that's what you do with the simulation on to save time and resources. Thermodynamics model selection. So the quality of a simulation strongly depends on the quality of data and parameters of the model used. Garbage in, which is garbage out. So thermodynamics selection is so paramount in simulation. If you mess up as far as selecting these thermodynamic models, then your model is useless. It cannot replicate whatever is happening within the real world. Data quality and availability are two of the most challenging issues in many simulations. So you usually draw from experience, or you have to do your literature research for you to select that particular thermodynamic model. Simulation software used in chemical process design contains many databases of material properties data and phase equilibrium data, particularly for convectional components. However, in many cases, independent experimental data are very helpful in the results verification. That's when commercial simulators become relevant, because they have robust data of this independent experimental data. And these are not readily available. That's why they are selling their licenses. And they can become more very expensive. In addition, for all non-conventional substances, the material properties data and phase equilibrium data are missing. So like for non-conventional substances like crude oil, because it's not a pure substance, right? So you cannot always find the needed data in a simulator. Sometimes you need to do experiments. Also, phase equilibrium data are not available for all possible binary pairs of convectional components. Another type of required data is the chemical equilibrium data and kinetic parameters of chemical reactions. This one in particular, they are very hard. You need to do your literature research to get these, or do experiments if they're not available in literature for new reactions. Simulation software usually contains a property analysis tool which can help you to choose your thermodynamic model, but usually it's not that accurate. These tools are used for detailed property analysis of pure components and binary antenna interactions. So I will dive deeper into thermodynamics selection on the next lecture. Please comment, like, and subscribe to my YouTube channel. Also consider clicking the link in the description to support my T-shirt sales business. Thank you so much. You take care.